have to open the slideshow.
Huh? Yeah, yeah. I'm just preparing. Okay, hey, whoa, that was loud. I'm Kat again. I think most of you were at my previous workshop. But today, right now, I'm going to talk a bit about Aztec, Aztec's infrastructure, a little bit about Aztec NR, which is how to develop smart contracts using our language Noir. It's a pretty different intuition from writing circuits with it. You don't have to think about like what you're proving, and you're working with state and stuff, so it's a different kind of thing. I do want this to be like pretty interactive. I haven't prepared too much, so if you have questions, please just shout them out or put your hand up or something. Yeah, so I'm gonna talk about just like an overview of Aztec architecture and infrastructure and how it works. So for those of you who aren't really familiar, Aztec is a privacy-first layer 2 on Ethereum, where you can have both private and public state and functions. So I'm just going to talk a bit about how that actually works. We use client-side proving. And then I'm going to code a bit in Aztec NR, which is like the Aztec framework for writing smart contracts in Noir. So you can see a bit of how that works and what that looks like and the intuitions for that. And then I'll talk a bit about like what is actually happening. There's a lot of abstractions in Aztec NR. Obviously, they're actually converted into circuits like under the hood if you're doing anything privately. So I'm going to talk about what that actually looks like and what's happening there whenever you're writing functions and executing them in Aztec. So this is Aztec. We got two like parts of it. There's everything that happens on the user device. It is obviously like paramount to privacy to have things on the device and executed locally. And then we obviously have some stuff that's on chain as well, which is kind of similar to EVM kind of things. So whenever a user interacts with Aztec, you know, they're going to be using like Aztec.js or potentially CLI or Python or something, or wherever we might have, and that's going to interact directly with something called a private execution environment, or PXE as we call it, PXE. So that runs like locally on someone's machine. It contains their database of keys, their UTXOs, their notes. We'll talk about that in a second. ACIR simulator, which is just going to be like what simulates transactions and proofs, and then also their circuit, the private kernel circuit, and that's going to be what actually generates proofs of functions that's happening privately on their PXE. Then once these proofs are generated, they are like sent over to the sequencer or the sequencer like network, and the sequencer will put all these functions in order and be like, yeah, this is what's going to happen, and this is how the states are going to change. And then they talk to the prover network, and the prover network will bundle all of the public transactions that have happened with all of the private proofs, generate like this full kind of proof, and then submit it to the Aztec network and Ethereum, roll up to Ethereum. So that's kind of how it works in a nutshell. The PXE is, it can kind of be run like, it's pretty much just like a node environment, so you can run it on your machine, or you can run it within a wallet. That's potentially what it might look like. And what we probably will expect to happen is that some people might not want to run it locally, and we'll have like different levels of privacy, and you know, you can run it locally if you want, but there'll probably be some services out there that lets you run a PXE in the cloud or something and use that. So there'll be different like, you know, differences between UX and privacy, and we'll see how that turns out when we go live. But this is how it works. For private state, I'm sure most of you are familiar with UTXOs. It's how most private chains work. It's how Bitcoin works as well. And it's the only way that actually really works with privacy. So an original like account-based models like Ethereum, you just have an account and you update the account. But whenever you go to update it, whatever account you're updating is going to be exposed because you're updating this specific account. And it's pretty clear. You're exposing the function that you're executing and also the value of what you are modifying. So instead of using that, we use UTXOs on private state, which is just kind of like two different trees. We have a tree of UTXOs, what we call notes, and you're always adding to those. And then we also have a tree of nullifiers. So if you're wanting to spend a UTXO or spend a note, you just create a nullifier for it instead of modifying this UTXO directly. So it's not clear exactly like what you're updating, what accounts are being updated, or what functions you're running. Like say I have 5 ETH and I want to send 3 ETH to my friend. I would like nullify my 5 ETH create a 2 ETH for myself and create a 3 ETH for them, and then they get their 3 ETH, but nothing is like deleted. There's just a nullifier for that 5 ETH in the first place. So it's important to be aware of that, but when you're working with public state, it's pretty much just like how EVM works. So there's a difference between private and public state, and that hybrid state is kind of interesting. We also have fun accounts on Aztec. We have like native account abstraction, but what's really cool about it is that usually with like 4337 and most account abstraction models is there's an entry point, some sort of like entry point contract that you have to go through, and they're going to be the ones that are verifying and executing the transaction. But because we can use the power of zero-knowledge proofs, as long as the entry point is private, as in it's generating a zero-knowledge proof, it can be anything. So there's a lot of like flexibility and privacy that you can have with accounts on Aztec, and it's pretty fun. Like anything can really be an account contract, as long as you're calling some sort of private function to verify the transaction. So yeah, this is what a transaction would look like. You've got, this is a private transaction, so you're just giving in like private inputs, the private state that you have in your Pixie, public inputs, and also like whatever private function that you're wanting to execute. Then we've got a kernel circuit that will like generate the proof that this transaction has gone through, and it creates this transaction proof, and then also whatever state needs to be updated publicly, it will generate that as well. So this all happens locally on your machine. These inputs, you can have like public inputs. So this is things like, say you want to maybe say that you are like from the US or something, and you don't want to reveal any other parts about yourself. The public input is the United States, but all the private inputs might be things like other stuff in your passport that you don't want to reveal. Private state, this is state like stored as UTXOs on Aztec, but they're private, so only you can decrypt them. Yeah, like if you might have like a private token or something, then your token would be private. So it's on the state, like it's in the UTXO tree, but you only have the key to be able to get it. Private inputs, so yeah, like passport data, like I was talking about. So other things that, you know, if you're trying to prove that you have a passport from a certain country, you don't want to reveal the rest of the private data from the passport, things like that. And then also functions. So this is kind of cool about Aztec, is that if you have a completely private smart contract, you don't actually have to deploy that contract to the chain, because you're proving that the bytecode ran successfully, like what it actually says in the contract. And like if you know, you're just interacting with someone else, they just need to have that bytecode, and you have it, and then you can do this together without having it on the chain, which I think is really, really cool. But yeah, you can have private functions without those functions ever being deployed to Aztec. So there's, yeah, I was talking to someone about like using this for insurance. So say they have algorithms that they don't want to be public about how they compute insurance premiums for people. They could just do that completely privately. It never has to be published anywhere. No one has to know how that algorithm works, but they can prove that it's a fair algorithm, and then it's the same algorithm that's being applied to everybody. So when we were designing the framework on top of Noir for building this, like it really, there's just a few different requirements we went through. So it has to feel like you're writing a smart contract, not that you're writing a bunch of stuff that's going to be proved privately, and then some of it's going to be like proved publicly and not zero knowledge, and some of it has to be encrypted and some of it isn't. Like we just has to feel like I'm writing a smart contract. It feels like, kind of feels like Solidity. It just feels normal. But we also want to be able to abstract away a lot of that private stuff. It's like it's all just UTXOs. You're just adding a bunch of things to a tree, adding a bunch of nullifiers. And we're trying to abstract away from that, but also make it kind of aware what you're working with. Because working with private state is obviously going to be different to public. And we're trying to get it to feel like as close and as simple and as possible. And then also like being able to switch state or play with state on both private and public, maybe like move it between each other. Like we think that's really important for tokens, and you know, maybe you have an NFT that you don't want to be public yet, but then there's like some sort of airdrop and you're like, hey, let's publicize this NFT, and you just make it public. you like unshield it. That's a really, really interesting thing technically of how that could work, but we want that to be possible. So that kind of like hybrid state and calling public and private functions from each other is something that we're trying to do. So, how much time have I got? We have 3 different types of functions on Aztec. We have public functions. These work like EVM works. You're just directly updating state. Running public functions, everything is public. Anyone can see what you're doing there. We also have private functions. No, unconstrained functions. These are not, no proofs are ever going to be generated for these, but they're kind of like things, say you just want to interact with your Pixie. You just want this app to know that you have 2 ETH or something, but they're not like, it doesn't really matter that you have that. Then you have this unconstrained function. And then what happens after that maybe is that they send that to ETH and that will be constrained, but just like getting it from your Pixie, it's quite interesting because because you have all of this stuff locally, like saying you have something it's really, really difficult to just constrain that because you could just input something into this function, like I actually have 5 ETH, and you can't constrain that because that's a problem. So they say unconstrained functions, and you would have to like work with Noir circuits if you wanted to prove that you do have 5 ETH or an NFT or something. You can write a circuit that then is like provable on the Aztec network. So yeah, it works with Noir circuits too. Wait, I should have private. Where did my private thing go? There's also private functions that I don't have a slide for. Private functions are just proved in the private kernel circuit. Every function that you write in Aztec NR that looks like a smart contract is translated into like a Noir circuit, and then that runs as a function circuit in your kernel. Yeah, so private functions directly correspond to private function circuits. Even if you have one smart contract, that's going to be like so many circuits in one, but it just looks like one contract. Public functions are executed in the AVM, similar to EVM, and private kernel circuits verify the private function execution of those private function circuits. They're proved in this like private kernel circuit and then batched together and sent to the sequencer. So, want to do some coding. Do you have a question? No. Okay. You look excited. I'm not sure if people are going to be able to follow along. If you want to follow along, do you want to follow along? There's stuff that you'll need to install, though. Okay, cool. If you do want to follow along, all right. Go to this GitHub repo. Why do I not have this here? I do. Go here. You have it already? How do you have it already?
He's a smart guy.
Okay, you figured that one out. Also go to Noirlang and follow the getting started to install Nargo. And go to Aztec Network, guides, quick start, and run this. Okay. I'm not sure you're going to be able to follow along, because we're kind of running out of time already. Yeah, so we're going to code easiest private voting contract. This is the simplest possible thing that I could think of, and then it got more and more complex because we added some stuff. But this kind of indicates like private and public transactions a little bit. So we're going to have stuff in private, so who you are will be private. It'll be anonymized. And when you call this cast vote function, you will be emitting a nullifier to say, I'm not going to be able to cast this vote again. Then that function will call add to tally public. That's going to be a public tally. It's a public function. Anyone can see that it was called, but they can't see who called it. And then we're going to store all this stuff in public because it's the simplest thing to do. If you're working with private and public state, you have to, because the Pixie is like not aware of its outside environment, and the outside environment is not aware of the Pixie. So you can queue up transactions to happen from private into public, but you can't do the other way around, and you can't like wait for a transaction to happen and then get it back into private, because you have to send it over from private to public. So that's why we're doing it this way. So, all right. If you're coding along, this is Aztec v Summit repo in the starter branch, and then I'm just gonna like turn it into the main branch pretty much. highlighted in the noir one, if you were there for that workshop too. Whoops. Okay. Probably need to sit for this. So this is a contract with some stuff that hasn't been filled out. Can you read this?
If you could make it light.
How do I change the theme?
I would try comment K probably. Or comment shift K. Appearance.
I haven't changed this theme in years. Right. Trying to do like preferences or something. Theme. Boom.
Oh, let's go.
There we go. That's gonna be the hardest part of it. Okay, so this is set up fairly similar to a WAR circuit in that we have our source directory with our main NR in it, and then this is our contract. And then we also have a NAR toml, which will just contain information about the contract. You have to specify that it's type contract and any dependencies. You'll always need this Aztec dependency, and we have some other abstractions you can use, like value notes and stuff that we can talk about. So what is happening here is that we are specifying it's a contract. These are the different like types and stuff that we're going to be using. And we will also play with keys a bit. Then this is the storage, just contract storage, similar to stuff in Solidity. So we've got an admin. It's a type of a public mutable, as in it's a public variable that is mutable. You can change it, of type Aztec address, which is just like the type of the address that exists on Aztec. We have a tally, that's going to be our vote. So it's a map that maps a field, so just like kind of an integer basically to a public mutable. So this is something that is also changeable, and that's also a field. So it will look like the candidate is number 1 and it has 5 votes, and this candidate is number 2 and it has 7 votes. Then we have vote ended, it's a Boolean, it's also public mutable, and we have active at block. So this is when people can start the vote. Why we have to use this is because of the way the keys work on Aztec. So we have everyone has like a nullifier key, which lets them nullify a note. But there's an ability to actually change that nullifier key. So say your account gets compromised in some way and you want to keep your account, but they have the nullifier key, then you just have to change the nullifier key and you can continue using your account. But if in this voting scenario somebody voted and then changed their nullifying key, then they could vote again. So what this does is we'll take their nullifier key that existed at that active block and then make sure that it has been nullified and they can't vote again. So I'm just going to get this up. We also have a constructor, which is similar to how things work on Solidity. So this is just like setting things up when it runs whenever you deploy it. So you're going to pass in whoever the admin of this vote is, write it to the public state that they're the admin. You're also going to write that the vote ended is false, and say that the active at block has been initialized with whatever block number currently exists. This is a function that I'm going to code now. So this is the private function of casting a vote. So pretty much what it's going to do is just generate the nullifier, make sure that the nullifier key, get the nullifier key from the active at block, and then push that, make sure it hasn't existed before, and then it's going to call add the tally public, which will just change the public tally of the vote. And it's an internal function. You can't just call this. It has to be called from cast vote. Then we have end vote as well. All that does is just update the storage here to say the vote has ended. And then we have an unconstrained function for getting a vote that just reads we pass in the candidate and it just returns the number of votes that they have. It's unconstrained because it's like you kind of will use unconstrained functions if it's just like a read function and you're not constraining anything towards it. We do also have like read functions if you're reading the chain, but you're going to be constraining something for it. So if we go to this, let's do cast vote first. Just have this on my phone so I can copy it if I mess up. All right, so we got to get the header, the block header, at the block to make sure that nullifier key is not changed. So we're going to do context get header at and pass in the active at block from the storage that we have up here. And then to read from private. So now we have our header that was at active, yep. And then we can get the message sender. MPK hash is like their nullifier public key master hash. So we can get that from public state, and then we can like use that to request their secret key. So we'll do get historical public keys. This is a function. And then we'll pass in the header at active block. Okay. What we just got before. And we also have to pass in the message sender. This is their key that we want. And we will get their nullifier public key hash. And then we can get their secret from this public information. We'll just do let secret, context, request, nullifier secret key for this specific app. And we'll pass in what we just got here, message sender, MPK and hash. And then now we can actually generate the nullifier. So we'll do let nullifier, kind of call the standard function of Peterson hash. And we'll hash together the message sender. Let's make that a field. The secret, oops. And then we can push that nullifier. So we'll just do context, push nullifier with nullifier. Is that popping up? No, okay. And then we can actually call this function here to add the function, the tallies to the public. So voting, the name of the contract is voting, so we just do voting. And then we get the contract address that this exists on. So we'll do this address, that gets the contract address. And then we're calling add the tally public. Yeah, passing in candidate. And then we're enqueuing it because we can't just set this up. And then in order to enqueue something, you have to pass in the context. So this context variable, by the way, is something that's like revealed when you use one of these macros. So this is pretty much just telling the compiler that this is a private function, and it's revealing any sort of private context, so like message sender or the address of the contract, and a bunch of other stuff like that. And same with public, you're passing in like exposing context there, so that's why we're using it here. Yeah, so now we can do this public function. So we will just, it's pretty easy. We can just firstly assert that the vote hasn't ended. So we can do storage vote ended, read is false. And if that fails, we can just do vote has ended. So this will error out if you try to vote when it's ended. And then we can create the new tally, and we'll get the information from get the tally that's at the candidate in this map, read it, n+1, and then we can just write that to the storage. storage tally at candidate writing tally. I typed this right, didn't I? Cool. I'm concerned that I've typed this wrong. Oh, there we go. So yeah, we've just got the nullifier key from the, we got the nullifier key that existed at the block that was active whenever this person is calling it now, and created the nullifier with that nullifier key. And then this will fail if the nullifier like already exists. It'll just be like, you can't do that again. And then it's calling this public function and fishing a new thing. So let's see if this actually compiles. Fingers crossed. Am I in that place yet? cd Aztec nargo compile. Sometimes there's just going to be a bunch of warnings. This is like in very active development, so there's a lot of warnings about stuff. Like things like, I know storage quite often has a lot of warnings because like we're not actually implementing storage in every single function. That's abstracted and done for you. If you know Rust, that might be a little bit strange, but we're using this storage word because we've defined it up here as Aztec storage. So yeah, now we have our JSON. It's been compiled properly, and we can play around with it. So when you install the sandbox, which I need to run actually, 1 second. Oops. Okay, that's concerning. I'm going to reinstall the sandbox. So the Aztec sandbox is just like, uses Docker and runs an Aztec network and Node and Pixie locally. So I'm just reinstalling the sandbox because for some reason it doesn't seem to think it exists, which is a little bit worrying. But you can deploy contracts to the sandbox, which is what I'm trying to do. So I can show you how the CLI works. Okay. Okay, well, that's going on. I think I'm actually out of time. But this is a bit about what's actually happening. So whenever we do private functions, whenever we mark it as like Aztec private, we're injecting this private context inputs, which is like things like message sender, the storage contract address, the function selector of what that function is, and just various different things that the compiler needs to know. You're also passing in like the chain ID and any sort of settings about gas limits. The historical header, so just like what is actually the header of the chain while you're doing this function. And then any sort of like inputs that are being passed in, it hashes them, and then that actually becomes one of the circuit's like public inputs, because you're saying this is what I want to expect back from it. Yeah, the return types are the inputs for the next circuit. Yeah, and then whenever those like function circuits are generated, then we also have the private kernel circuit, which receives the proof of those function circuits and the public inputs, including the returns, and it verifies that those returns are actually accurate, and that the function exists, and that it's been like computed properly. For public functions, it initializes like basic context stuff, like the chain ID, contract address, the message sender, any other information that might be needed, and the function arguments. This is very similar to like EVM stuff. So yeah, public inputs are just the public inputs, the function arguments. The AVM, Aztec virtual machine, processes it on the sequencer, and then everything is visible on chain for these ones. So whenever the result is good, it's passed to the public kernel circuit, which is not actually a zero knowledge circuit. It's just a regular circuit because all the information is public. Do I need to talk about this? No. Yeah, for unconstrained functions, like the one that we did where it was just get the vote at a candidate, You are generating like the execution environment in the Pixie, getting the information from your private execution environment, and then executing the function in your ACVM, which is like the machine like inside your Pixie. And yeah, no kind of circuits or constraints are happening inside there. Okay, I'm out of time, and I don't know if my sandbox is working. No. Okay. Yeah, I got some issues with Bash. I think I need to update my.
But if you run it directly from Aztec.bin, it would work probably. But /bin/Aztec.
Oh yeah. No. I'm just gonna deploy it so you can see what that looks like. I'm not gonna play with it.
Right, but in the meantime, thank you, Kate. I believe we have like time for like one short question, I believe so. All right then. Thank you, Kat.